Let us continue our discussion of Chapter 1. The other major part of Chapter 1 is scientific units and measurements. After all, chemistry is a quantitative science as much as it is a qualitative science, so we need to review the proper units to use. So as you probably know, we use what's called the English system of units: yards, miles, feet, inches. And there's a system called the metric system, and that's what we are going to use in this class. You used it in lab early this week, and so you're somewhat familiar with it. The metric system, as I said, has common units that we'll use. You have to learn these symbols. That's meters, kilograms, nanometers, Kelvin, centimeters, micrograms, dealing with mass, length, temperature. These are much more useful to us than the English system, because these are almost all based on powers of 10. We're not going to use miles or pounds for weight. We're dealing with mass anyway. We're not going to use inches. We're going to use centimeters and meters. We're not going to use degrees Fahrenheit. We're going to use degrees Celsius. We're not going to use ounces. We'll use milliliters and so forth. So a physical quantity that we measure is meaningless without a unit. So if I wrote down the number 93 million, for instance, that would have no meaning if I didn't put a unit on it. As soon as I put a unit on it, now I say, oh, that must be the distance from the Earth to the Sun. You always need a number to specify a physical quantity and a unit. So units are just as important as the numbers themselves. You might express something large like that, or you might need to express something small, like the size of an atom, which would be something like 9 zeros and the number 1 meters. You got the number and you got the unit. So never leave units off numbers. So I want you to learn the SI system. It stands for Système International. It's French. Système International des Unités. So we call it the SI system for short. Some of the common units that we're going to use, there are 7 base units. We're only going to use a few of them. So here are the important ones that I want you to, important units I want you to learn. Important metric and SI units. So this could either, there's a slight difference between SI units and metric units. But you can think of them as all one grouping. So we're going to deal with mass. The SI unit is a kilogram. The metric unit is a gram. And the equivalents are 1 kilogram is equal to 1,000 grams. Pretty straightforward. If you want to relate that to the English system, a kilogram is about 2.2 pounds, roughly. We're going to, one of the other base units is the length. So the SI unit is a meter. The metric unit is also a meter. 1 meter is equal to 3.28 feet. A little bit longer than a yard. Another unit that's important to us is actually a derived unit, volume. The standard unit, the SI unit, is a cubic meter. The metric unit is a liter. 1 cubic meter is pretty large. It's 1,000 liters, about 262 gallons actually. Temperature is another base unit we're going to deal with a lot. The unit in the SI system is a Kelvin. The base unit in the metric system is a degree C. But the nice thing with these is that 1 kilogram is equal to 1 degree C. 1 degree Celsius is equal to 1.8 degrees Fahrenheit. So a degrees C is actually a little bit larger than a degrees Fahrenheit. We also have what are called derived units. Derived units just means they take one of these base units, like these, and combine them. So for instance, we're all familiar with speed. Speed is equal to distance divided by time. And in this country, we deal with miles per hour. In the SI or metric system, we're going to deal with meters per second, right? Written like that. Another important derived quantity we use all the time, you used it in lab with the density of egg, is defined as the mass over the volume. And common units are grams per cubic centimeter, which is equal to a gram per milliliter. But we can also use grams per liters to specify the density of gases. These are used for solids and liquids. This unit is useful for gases, and the reason is because gases have such a low mass, it takes a large volume to make a reasonable number to measure, so we use grams per liter. You can even have derived units in physics are important. If you look at the equation E equals mc squared, if you plug in the standard units for that, mass is kilograms. C is the speed of light, so it would be meters squared per second squared. That actually turns out to be what's called a Newton meter, which is also called a joule. So these are all derived units, and you'll need to be very comfortable using them as well. Now, another thing you have to be able to do is you have to know the relationship between different metric prefixes. So learn these metric prefixes because it'll just make your life a little bit easier. So we have very large ones like mega, which is a capital M. That stands for 10 to the 6th, or a million times anything. So a megameter, for instance, would be written like that, which would be 1 million meters, written like that. So the prefixes are nice because you don't have to write out all those zeros. You can write it in scientific notation like that as well. Kilo is a very common prefix we'll use. It's actually a lowercase k. That stands for 1,000, which is equal to 10 to the 3rd. So a common thing is a kilogram. That's a unit of mass, which is 1,000 grams, as you know. Some of the other common ones is the prefix deci, which is a lowercase d. That stands for 1/10. So that's something multiplied by, that's a tenth of something, which is also 10 to the negative 1. So for instance, a deciliter, D capital L, is equal to 1/10 of a liter. Centimeter, very common, or centi, I should say, which is lowercase c, and that's 1/100th of something, or 10 to the negative 2nd power. And that would be obviously, like I said, a centimeter or a centigram. You can say that. There's 100 centimeters in 1 meter. Then another common unit is milli. Lowercase m is the prefix, so please don't confuse milli with mass. Some of these letters, we only have 26 letters, so they have to double up their use once in a while. A milli is 1/1000th of something, which is 0.001, 10 to the negative 3. So a milligram would be written like that, and that's equal to 1 milligram would be 0.001 grams, like so. Micro, now we're going into the really small. Micro has an interesting symbol. We already used M for milli, so we use the Greek letter M, which is called, we use a letter called mu in Greek. And it is looks like a U with a little curl on the front. That's 1/1,000,000th of something. So 5 zeros and a 1, which is equal to 10 to the negative 6th. Where would micro be useful? Like in the length of something, a micrometer. 1 micrometer, written like that, is equal to 1/1,000,000th of a meter. A micrometer would be like the width of a human hair or something like that. Nanometer, now we're getting down onto the atomic level. Nanometer is a lowercase n, which is 8 zeros. And you can see now it's very inconvenient for me to write all those zeros, so I'd rather write 10 to the negative 9th like that. And 1 nanogram is equal to 10 to the negative 9th gram. So that's 1 billionth, not millionth, billionth of a gram. Very, very small. Pico would be a useful prefix to use when we're talking about atomic sizes, and that's a lowercase p. And that's, I won't write all the zeros, that's 10 to the negative 12th. 1 picogram, written like that, is equal to 10 to the negative 12th grams. And that's about it. Those are the common prefixes we'll use. So let's continue. We'll talk a little bit about a few of the units in more specifics. First of all, mass. Mass is the amount of matter in an object. Now, please don't confuse mass with weight. Weight is not mass. Weight is a measure of the gravitational force acting on an object. If you wanted to relate the two, weight is equal to the mass times gravity. That's why you weigh less on the moon. This is a sample of a mass. This is a 50 kilogram mass. It's got some weight to it. I mean, I feel its weight because it's being pulled down by the force of gravity. But this would have the same mass in outer space as here. You just wouldn't feel it is heavy in outer space because the gravitational pull is much lower. So weight depends on location and gravity. Mass is independent of that. Mass never changes. The standard mass, see, all these fundamental units like mass are based on standard things. They have to have a reference. The reference mass, I believe, is kept in France. It's actually a kilogram cylinder made out of platinum and iridium. It looks something like this. It's quite a bit bigger. It would be about 20 times larger than this, but it's kept in a very safe place under almost a vacuum, because they don't want air to get to it to oxidize the surface, because all scales in the world are calibrated relative to that mass. They make replicas of it to distribute around the world, but the standard one is kept in France. So, for instance, the difference on Earth, for instance, I weigh 180 pounds, but on the moon I would weigh 30 pounds. So that's weight. That changes. Weight changes. On Jupiter, I would weigh 430 pounds because Jupiter's weight Jupiter's gravitational field is much larger because it's a much larger planet. Gravity is a function of the size of the object that you're on. When people say they're weightless in space, that's not really true. They're only weightless because they're free falling around the Earth. They're not feeling any upward push. You feel weight because the floor is pushing up on you. If you ever had, if you go in an elevator or on a roller coaster, you feel weightless when there's no force pushing back on you up from the floor. But you still have the same mass. We measure mass in lab with the balance. It's either what's called a triple beam balance, but the more useful ones are the digital balances that are precise to anywhere between 2 and 4 decimal places. So these are electronic balances, much more useful to us. We just read the mass directly from the display. Some of the extremes of mass that we encounter in science are things like, oh sorry, I spilled some of my weights there. An atom of gold has an incredibly small mass, as you might imagine. It's 3.3 times 10 to the negative 22 grams. A mosquito weighs about 2 milligrams. An elephant weighs 5,000 kilograms, which is, 10,000 pounds, I believe. And the Earth, we can actually calculate the mass of the Earth. It's roughly around 6 times 10 to the 24th kilograms. So you can see very small numbers to very large numbers. This is why scientific notation, which I will review with you in a little bit, is really important to be comfortable with. So these are some of the units of mass that we use all the time. We want to use kilograms. Gram is the most useful to us in lab because the balances that we use always display mass in grams. So The display that's displayed on these balances is always in grams, because a gram is just the most useful size mass that we can use. We can use milligrams or micrograms, but we have to do some metric conversion. But just to relate again, 1 ton, which is 2,000 pounds, is about 907 kilograms. A pound, which we're all very familiar with, is about 454 grams. What's a 1 gram mass look like? I have it in here. I think it's this little guy. No, it must have fell out. This is a 2 gram mass. You see, it's really, really tiny. So grams are really small. It takes a lot of grams to make something as small as a pound even. The other useful unit is length and volume. Let's continue with our next important base unit, which is length. In the SI system and the metric system both use the meter as their base unit. So everything is either a centimeter or a millimeter or a nanometer. That is all the metric prefixes will be applied to a meter to define length. And unlike mass, remember, mass is defined relative to a real object. It's a kilogram mass kept in a lab somewhere. But everything else, including length, is defined relative to a standard in nature that never changes. The standard they chose for length is the speed of light. The speed of light is approximately 186,000 miles per second. That's an approximation. But they've actually figured out the speed of light to high precision. And when you do a little algebra, you actually can convert the speed of light into how far light travels in a meter. You can define a meter as how far light travels in a fraction of a second. And that's where this number comes from. Light travels 1 meter in a very, very small amount of time. So if I can show you where the speed of light comes from that fundamental, from that fraction. If you just take 1 divided by 299,792,458, you get, well, let me convert that to scientific notation, you get 3.3356, etc., times 10 to the negative 9th. Well, if I take the reciprocal of that, press 1 over x on my calculator, I get the speed of light, 2.99792,458. So what does that mean? Speed of light is incredibly fast. If I wrote that out, it would be 299,792,458. That would be times 10 to the 8th. 1, 2, 3, 4, 5, 6, 7, 8. So that's meters per second. That's the speed of light. A roughly 300 million meters per second, which is about 186,000 miles per second. So that never changes. That's why we define meter relative to that. Now another, before I move on to the next unit, just here's some common conversions using the meter. A kilometer is a little bit, quite a bit more than a mile, 0.62. Actually, it's not quite a mile. It's a little more than half a mile, 0.6214 miles. A meter is about 39 inches, as I said. A yard is a little bit less than a meter, and so on. We're interested in very small units of length in chemistry. So, for instance, the radius of a hydrogen atom is incredibly small. We have ranges of length that go from the tiniest diameter of a hydrogen atom, 2.4 times 10 to the negative 10th meters, to the circumference of the Earth, which is around 24,900 miles or 40 million meters. This diagram is interesting. This shows you how we fit into the relative size of the sun and the nearest star. So these scale models help us kind of understand like how the size of the solar system and sizes of atoms and things. So I'll use this analogy quite a bit. If you shrink the sun down to about the size of a tennis ball, then the Earth would be smaller than a grain of sand, and it would be 19 feet away from the sun. So that kind of puts it in perspective. That's really the scaling of how we are that small relative to the sun. If you just look at the nearest star, which is called Alpha Centauri, that would be, on that scale, 890 miles away from us. And it takes light a little over 4 years to travel from the nearest star to here. It takes about 8 minutes 20 seconds for light to reach us here on Earth from the sun. And so you can see our nearest star is incredibly far away. It's about 25 trillion miles away. But as I said, in chemistry, we're going to deal mostly with very, very small distances, the opposite end of the spectrum. The other important derived unit that comes from length, so it is volume. Volume is a derived unit. It's length times width times height, just like you calculated in the density of an egg lab. There's some important conversions for volume that I want you to be comfortable with. A cubic meter is the sort of the standard unit, but it's such a large unit it's not that convenient. That's defined as 1,000 liters. And a liter is a little bit more than a quart, because a gallon is 4 quarts, and it takes a little bit under 4 liters to make a gallon. All these other things are just conversions between different metric prefixes, not terribly useful to us. 1 fluid ounce is about 30 milliliters, so a can of soda is 12 fluid ounces, so what would that be in milliliters? 12 times 29.57. A can of soda is about 355 milliliters. And I always picture a milliliter about the size of a sugar cube. It's pretty small. And this is an important diagram too. I think your book has something similar. Let's just read through it. The metric system is based on factors of 10, and it's much easier to understand. So here's how we come up with the fact that 1 milliliter is equal to 1 cubic centimeter. That's a very useful conversion between distance cubed, the fundamental definition of volume, and a volume using the metric system. So here's how it works. You take a cubic meter, the fundamental unit of volume, and if you divide each side of the cubic meter into 10 pieces, which is this little bluish cube here, that would be 10 centimeters long, because 10 plus 10 plus 10 plus 10 and so on is 100 centimeters, which is a meter. So let's imagine we're taking that out, and now we have a meter cubed is 1,000 of these, 1,000 cubic decimeters. And we've defined a cubic decimeter to be a liter. We just call it a liter. We made that word up. So if you take this liter or cubic decimeter and break it up into 1,000 little pieces, you'll have on each side, since it's 10 centimeters, if you divide 10 by 10, you get 1. So each of those little cubes, which is a red one, we pull that out, that's 1 centimeter on a side, length, width, height. So that little red cube is 1 cubic centimeter, and there's 1,000 of those in there, and there you go. There's 1,000 cubic centimeters in 1 liter. 1,000 cubic centimeters equals 1 liter. And since another way to say a liter is 1,000 milliliters, the thousands cancel, and we come up with the fact that 1 milliliter equals 1 cubic centimeter. Again, that's useful, especially when you're talking about density of an object. You can express the density of an object as either grams per cubic centimeter or grams per milliliter, and they're the same thing. Some of the devices we use to measure volume, we'll use all the time in the lab: graduated cylinders, volumetric flasks, burettes. This is called a volumetric pipette. We can use syringes, but we'll find the most useful objects to be a graduated cylinder and burettes. So another very important unit we use all the time in science and chemistry is temperature. So you can think of temperature as how fast atoms and molecules are moving. It's a reflection of the energy within a system. So the common units we're all familiar with of temperature are, in this country, we use degrees Fahrenheit. The metric and SI system use degrees C, or this new unit you probably are not very familiar with, which is called a Kelvin. and that's spelled lowercase Kelvin. That is the SI unit of temperature. The reason why the Kelvin scale was invented was because in many equations we have temperature, and we cannot have a negative value for temperature plugged in, because then the equation wouldn't make any sense. And so on the degrees Fahrenheit and degrees Celsius scale, you can have negative temperatures, and that is not going to work. The equations kind of fall apart. So the nice thing is, though, is that the size of a degree Celsius is the same as a Kelvin. The only difference is where the 0 point is defined. So 0 Kelvin is defined as negative 273.15 degrees Celsius. So if you want to convert temperature in degrees or to degrees Kelvin, you say you take the temperature in degrees Celsius and add 273.15 to that number. So room temperature would be about 298 degrees Kelvin, or roughly 300 Kelvin. The boiling point of liquid nitrogen is about 77 Kelvin. Just to give you an idea of extremes in temperature that we see out there, on Earth we're used to 60 degrees Fahrenheit with 90 degrees Fahrenheit, things like that. The temperature on the surface of Mercury is 662 degrees Fahrenheit. The temperature on the surface of Jupiter in the daytime is negative 166 degrees Fahrenheit. The temperature of the sun is extremely high. It's about equal to 5,510 degrees Celsius at the surface, and at the surface of the sun. And in the temperature of the core, it's about 15 million degrees Celsius. So you can see there really isn't any upper limit on temperature, because temperature, as I said, is just a reflection or an expression of the energy of things. So the energy of objects can be incredibly high, but the energy of objects can only get so low before all matter falls apart. So when you get down to negative 273.15 degrees C, which is called absolute zero, in theory, all matter is supposed to fall apart. We haven't actually ever been able to reach absolute zero in a lab, but we've gotten very close. The temperature of liquid nitrogen, for instance, is about negative 346 degrees Fahrenheit. So you have temperatures all over the place, but on our scale and in our labs, we're going to pretty much deal with just the degrees Celsius and the Kelvin scale. And there's a nice way to convert between the three scales and to kind of understand how they all fit together with a picture like this. So on the Fahrenheit scale, the boiling point of water is about 212 degrees Fahrenheit, not about, but exactly. On the Celsius scale, boiling point of water is 100 degrees Celsius. And on the Kelvin scale, the boiling point of water is 373.15 degrees C. Body temperature is about 98.6 degrees C, about 37 degrees Celsius, about 310 Kelvin. So notice I say degrees Celsius, but I say Kelvin. We don't use the word degree when we talk about Kelvin. If you go all the way down, the only point that the degrees Fahrenheit and the degrees Celsius scale are the same as at negative 40 degrees Fahrenheit, which is equal to negative 40 degrees Celsius. And again, absolute zero is the lowest possible temperature when all atomic motion is supposed to stop. And so that is on the Kelvin scale is just called zero. So you'll notice on the Kelvin scale there are no negative temperatures, which is why we use Kelvin in all the equations that we're going to use in this class. We'll use Kelvin because we want positive temperatures all the time. So if you are paying attention here, you'll see that between the freezing point of water, 32 Fahrenheit, and the boiling point of water, it's 212 minus 32, that's a 180 degree difference. On the Celsius scale, which is sometimes called the centigrade scale, So it's the old term people used to use is degrees centigrade, and that comes from that word centi is 1/100th, as you can see, and that's because there's 100 degrees between the freezing point of water and the boiling point of water. So 100 degrees Celsius or degrees centigrade covers the same temperature range as 32 Fahrenheit to 212, which is 180. So degrees Celsius is actually a little bit larger than a Fahrenheit degree, and that helps us develop it helps us derive the equation that relates degrees Celsius and degrees Fahrenheit. And I want to show you that right now. Let me just gather my notes here and make sure I'm not missing anything. So let me show you on this piece of paper here. It's pretty nice to be able to do this sort of thing if you ever want to know where these equations come from. So as you know, let me just make a graph here. Make a graph like so. And on this axis, I'll put the temperature in degree Fahrenheit. And on this axis, I'll put the temperature in degrees Celsius. Let me get another colored pen here. And we know that there's a couple true statements about how these two scales relate. The freezing point of water, which is 32. And this isn't going to be drawn to scale. It's 212 degrees Fahrenheit. So freezing point of water, boiling point of water. On the Celsius scale, it would be 0 and 100 between the freezing point of water and the boiling point of water. So let me just graph this point. We know that that's true. 0 degrees C is equal to 32 degrees Fahrenheit. And we also know that 100 degrees Celsius is equal to 212 degrees Fahrenheit. So let me circle that point. And let me draw a line between the two. 2 points make a line, so we can actually calculate then the slope of this line, and we can derive the equation that relates the Fahrenheit scale and the Celsius scale. So what do you need to know to define the equation of a line? You need to know the slope. The slope of this line is equal to the change in the y divided by the change in the x. So that, let's just start with this point. The coordinates of this point, I'll write over here, are 100 on the x-axis and 212 on the y-axis. The coordinates of this point are 0 on this axis and 32 on that axis. So the slope would be 212. I'll leave units out of this for now. 212 minus 32 over, that's the change in the y, divided by the change in the x, which is 100 minus 0. And that's equal to, that's 180 over 100. And if we simplify that down to simplest terms, 180 over 100 is the same thing as 9 over 5. Now we can take that slope down here and we can say, okay, I know that at a minimum, this is a y equals mx plus b expression I'm going to write, slope-intercept form. On the y-axis, I have temperature in degrees Fahrenheit, so I'll write temperature for degrees Fahrenheit. The y equals the slope I just calculated, which is 9/5, times the x-coordinate, which is defined as the temperature in degrees C, plus the y-intercept. So I don't know that yet. But if I'm looking carefully at this graph, I see that the y-intercept of a straight line is the point at which the line crosses the y-axis when x is 0. So when this is 0, I could have actually redrawn this graph a little bit better, but when the x is 0, the line crosses the y-axis. So when x is 0, the y-intercept is 32. So I can rewrite this equation as temperature Now I'll just write it subscript. Temperature in degrees Fahrenheit is equal to 9/5 times the temperature in degrees C plus 32. So that's a very important equation to use to convert degrees Celsius to Fahrenheit. And then you can just do a little algebra to convert that to the equation calculating degrees Celsius from Fahrenheit. All I got to do is move the 32 over there, so I get temperature in degrees Fahrenheit minus 32 is equal to 9/5 times the temperature in degrees C. I just move that over there. And now why don't I just multiply both sides by 5/9, like so. My water softener's coming on, so it's going to make it a little loud in here. I'm down in my basement. And this cancels with this. Now I have temperature in degrees C over here, and that's equal to 5/9 times temperature in degrees Fahrenheit minus 32. And that's the other useful equation. Now, how would we apply those? Well, how do you know that those are true? Well, I just proved it to you mathematically. But if you plug in, let's say, for instance, on this graph, just a mental check, plug in 0 degrees Celsius into this equation here. You see 0 here multiplies by 9/5, that's 0, and I get temperature to be 32, so it works. This is the same thing. Plug in the boiling point of water, which is 212. 212 minus 32 is 180, should be. If you take 180 times 5 divided by 9, you get 100 degrees Celsius. So right, the boiling point of water, which is 212 degrees Fahrenheit on the Fahrenheit scale, is 100 degrees, sorry, I'm out of scale, at 100 degrees on the Celsius scale. So be comfortable in relating all three scales. And when we use thermometers in the lab, we're going to primarily use degrees Celsius thermometers. And to summarize, the other important one, as I already mentioned, is the equation that relates Kelvin to degrees C. So take temperature in degrees C and add 273.15, and then you convert Celsius to Kelvin. And that's where you can see where absolute zero comes from. If you solve this equation for 0 on the Kelvin scale, you get negative 273.15 degrees C as the coldest possible temperature.